All right, as promised, I'm going to write up some notes here, and I'm going to give you some stuff for limits. What I'm going to look at first is this very first problem here. F of x is equal to x to the third minus 8 over x minus 2. This monstrosity right there. And the question is, what happens at x equals 2? Obviously, if I substitute in a 2 into this function, the denominator will clearly equal 0. Last time I checked, 2 minus 2 is definitely 0. And as soon as we know the denominator equals 0, we should still actually check the numerator. We should really check 2 cubed minus 8 and find out that, hey, that's 0. And what that does is it gives me this concept of 0 over 0. It's an indeterminate form. And we're going to talk about that more tomorrow. But the whole idea here is that anything that's 0 over 0 is going to be what's called undefined. It doesn't necessarily, it's going to be indeterminate. It doesn't necessarily mean that it's undefined. It just means that we don't know what it is yet. So at 2, we know that does not exist. Cool. So I'm just going to write D and E right here at 2. But what's interesting about this problem is it actually equals something. You see, using my calculator, I actually took that function, x cubed minus 8 over x minus 2, and I substituted in values as we approached from the left. So I substituted in 1.75 just to get an idea of what the graph was doing. And when I plugged in subbed in a 1.75, I get 10.563. Maybe not the most useful. When I sub in a 1.9, I get 11.41. And when I plug in a 1.99, I sub that in, I get 11.940. And when I substitute in a 1.999, I get 11.994. Interesting. Seems like every single time I get closer, that gap decreases, like I'm going to cap out somewhere. So then I said, well, if the left looks like it does that, I wonder what the right does. So I picked the number 2.5 and substituted that in, and I got 15.25. I substituted in a 2.1, I got 12.61. Oh, it's decreasing. That's kind of interesting. Substituted in a 2.01, I got 12.06. Well, you know, that's from going from 15.25 to 12.61. That's big, but 12.061, that's 060, that's not bad. You got 12.006. Wow, that really slowed down a lot. And what you should see, hopefully, is that it seems pretty obvious to me that as we keep going this way, and we come in this way, even though this does not exist, the limit of f of x should approach 12. Now, one thing I do want to point out, this will be read as the limit of f of x as x approaches 2 is 12, written also like this. You'll see down here we talk about left side and right side limits. That's going to be important. Or graphically put, you can see this graph. If I plug that into my calculator and look at this f of x, if I look at the left side limit, what I'm doing is I'm following the graph as I approach the 2. Now, what I was talking about earlier with folks is, let's say, I'm going to draw a little box here. A little box. Boxes are cool. If I approach the left side of the graph, essentially what I'm going to do is I am looking a little larger than I wanted it to be, but that's okay. What I'm actually doing is, it's like there's this black box over the 2. What I'm doing is I approach the limit as I approach 2 from the left, as I'm saying, you know what? I don't even care about what's happening over here. If I follow the line this way till x equals 2, does it look like I approach the 12? Likewise, have I come at it from the right side, now we're talking about the right side limit here. As we come in from the right on the graph and I get closer and closer to this 2 concept, does it look like the graph goes to 12? And you'll notice that both the left side and the right side both seem to be approaching the same number. Well, of course, you can see that that's the case. You can see that's the case, but there's a hole at 12. Because those two exist, we would say that the limit does exist, even though f of 2, oops, I don't want to move everything, f of 2 itself does not exist. Now that's not to say that a limit will always exist. Left side limits have a tendency of existing, and right side limits both have a tendency of existing. But even though the left and the right might exist, they don't necessarily have to be the same thing. Again, if I draw my little box back, maybe I can make it thinner this time. There we go. That's actually a very good box. I'm proud of that box. If I approach the limit, and I take a look at the limit from the left side, that means I want to get close to the 1. Limit as x approaches 1, so I'm getting close to the 1. And I look, and it looks like that graph should come right about here. You would say that that limit is a 1. The graph is tending in that direction. I don't care what the heck happens at the end of the line. I only care about what the graph itself is doing. Likewise, if I approach the graph from the right side, and I follow that, we'll see that that goes to 2. Now I'm going to put a situation out here. I say, okay, well, what's the limit if I don't put a direction on it? Limit as x approaches 1 of f of x. And I put a wager on there. I bet you that if $100, here's the deal. If you get this right, I'll give you $100. If you get it wrong, I'm actually, because this is such an easy question, I think I deserve, I'm a smart guy, I think I deserve a little extra if you get it wrong, because I'm giving you such an easy question. And I ask you, what's the limit as x approaches 1 of f of x, and you owe me $10,000, no one would take that bet. Reason being, well, which limit do you want, left or right? And I say, doesn't matter. Well, that's kind of how it works here. You see, if I come from the left side, it's 1. If I come from the right side, it's 2. We don't know what that number should be. And if those two numbers are not in agreement, the left side and the right side, we say the limit here does not exist. Now, of course, if the person comes up and gets rid of our coverage and apparently erases my two things, you can see right here f of 2 itself is 2. Now in this particular case, we say that the limit of as x approaches 1 of f of x does not exist because the left limit is not equal to the right limit. The left and right limits differ from each other. Now that's one of 3 different reasons why a limit will not exist. There are 2 more. One of them says that the function is unbounded. All that means is that the function goes to infinity or negative infinity. Now, I do want to point something out. We have a very bad tendency as mathematicians to try to shorthand things, and then we don't explain it to our students very well, and then we get this terrible misnomer. Please do not make the mistake that an infinity or negative infinity is a number, is a value that we're approaching. We're not approaching a value. That's the key. Infinity and negative infinity are not quantities that we are getting close to. What infinity and negative infinity are ideas that say that we're not actually approaching a value at all. We are getting really, really large or really, really small, but we're not going to a number. Sorry, I'm hungry while I'm doing this video. I won't do that next time. So, the other option is that we'd have something that's oscillating. In this particular problem, the limit as x approaches 0 of the sine of x. That particular graph is kind of a weird looking graph. And what it does, plug it in your calculator once we get them. It's kind of cool. Oops, you know what I realized? It's a terrible place to put that particular axis. Oh my goodness, come on board, don't do this to me. What this graph does actually is as we start from the outside, it's got these really beautiful, long, sweeping things, but as we get closer, and it starts bouncing up and down and up and down and up and down and up and down. And it starts bouncing up and down, up and down, up and down, up and down, and it starts oscillating super duper 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 fast as we get closer. It bounces between -1 and 1. What does it hit when we get to 0? Well, it doesn't matter, because as we keep getting smaller and smaller, we keep getting closer and closer and closer and closer to 0, which just means we oscillate between -1 and 1 faster. So we don't know what number to say. So we say that it is undefined. Now, talking about asymptotes real quick, here's a graph with an asymptote. Obviously, we can see there's an asymptote existing here at 2. If I ask you for the limit from the left side as x approaches 2, we simply follow the graph from the left side down to 2, and we'll see that this is negative infinity. Remember, that does not mean that that exists at negative infinity. We say that this does not exist and that it is unbounded. As we approach x, as we take the limit as x approaches 2 from the right side, and we follow that in an upward pattern, again, what's happening? It means that the graph is growing now. It's getting larger, but it's not going to a value. We say that's infinity, but that's not actually a number. It's a concept that means that it does not exist. We are unbounded. So in this case, you'll notice that the left and the right are not equal, so we simply say that the limit does not exist, and you can say a couple things. You can say unbounded, or you can say left is not equal to the right. That's what I'm going to leave it as. And f of 2 is going to be does not exist because, well, it's an asymptote. There's no point actually there. All right, good. One more thing then, real fast, as we go to positive infinity and negative infinity. Those are going to be important concepts, important things we have to deal with. As we approach positive infinity and negative infinity, those are the ideas that we are going outward like this as we approach, in this case, negative infinity. This graph is unbounded. Again, I want to make it very, very clear that we say that this technically does not exist. It is unbounded. Likewise, as we go positive infinity, see this graph decreases and we'll head towards negative infinity. That's not a value, so we say it does not exist. Unbounded. This differs a little from when we have horizontal asymptotes. We follow negative infinity. Please never try to get to negative infinity from the left side. You'll only want to cry. If we go to negative infinity, we'll see that that seems to be getting closer and closer to this line of 4. And if we go to positive infinity, we'll see that this line gets closer, this curve gets closer and closer to the line y equals -2. That's asymptotic behavior. All right, folks, hopefully if you were struggling, hopefully this gave you at least a little bit to work with. And hopefully you can make sense of what's going on there. I look forward to seeing you all tomorrow. By the way, I should have mentioned this earlier. Some of you have probably written down the notes now. But these notes will be provided to you as a skeleton copy of the notes tomorrow so that you can write down whatever you need so that you can be successful. Anything that I put up as a video, hopefully the goal is to eventually get you skeleton notes before I put up the video. So I'm trying to make your life as easy as possible. I told you it would be 10 to 15 minutes. It meant 13 minutes, so I'm going to stop here. Hope everything went well, and I look forward to hearing from you soon enough.